Hello, welcome back. Now we shall discuss how the sample size estimation is done using decision theoretic approach. In my PDF note, I have discussed how the total cost of the survey is modeled, and for that purpose, you require a loss function, a cost function, through which you can have the expected loss function and cost function, and by adding expected loss function and cost function, we will have the total cost function, and we will find the optimum value of n by minimizing this total cost. And in order to explain this, we have an example, and in this example you are trying to estimate the population mean in simple random sampling without replacement. And suppose the loss function is L of z is equal to lambda into z square. Here z is the error and L of z is an error function. You can have many loss functions, but for example we take this L of z is equal to a constant times square of the difference between y bar and capital Y bar. That is L of z is equal to lambda into z square, where z is equal to y bar minus capital Y bar. Definitely you know z is equal to y bar minus capital Y bar is an error, because you are estimating population mean capital Y bar using the sample mean small y bar in simple random sampling without replacement. So naturally this difference is of course an error. Okay, and you square this error and you multiply that with a constant. Okay, now for this particular loss function, we will see that the expected loss, that is L of n, is equal to expectation of L of z, that is lambda into expectation of z square. That is lambda into expectation of z minus z y bar lambda into expectation of y bar minus capital Y bar the whole square. Okay, and what is this? What is expectation of y bar minus capital Y bar the whole square? It is nothing but the variance of small y bar. And what is variance of small y bar? It is equal to 1 by n minus capital 1 minus 1 by capital N into a square, or n minus n by n into a square. We have discussed all these things earlier. So you multiply that variance with lambda, you will get lambda into 1 by n minus 1 by n into a square, or splitting, you will get lambda into a square by n minus lambda into a square by capital N. Okay, so this is the expected loss function. Expected loss function, that is this small l is the loss function and capital L is the expected loss function. And you know, expected loss function will be a function of small n. You can see this is a function of small n. Okay, capital N is a fixed quantity, but small n we don't know, and we have to obtain the value, optimum value of this small n. Okay, and in addition to this expected loss function, we need a cost function. For any survey, you can have a cost function, and here we consider a very simple cost function in the form C of n is equal to C0 plus C1 into n. C0 is an overhead cost, including stationery cost, printing cost, training cost, etc. And C1 is the cost of enumeration, and therefore C1 into n is the total cost of enumeration per total cost of enumeration for enumerating small n sampling units in the population, and plus the overall cost of the survey will give you C0 plus C1 into n. That is the cost function. Okay, then you add the expected loss function capital L of n and cost function C of n for getting the total cost. Okay, total cost T of n is equal to sum of the expected loss function and cost function, which is equal to lambda into s square by small n minus lambda into s square by capital N plus C0 plus C1 into n. Okay, then what is our objective now? Our objective is to minimize the total cost T of n. Okay, and as T of n is a function of small n, how do you find the minimum of T of n? Yes, you can differentiate T of n with respect to n, and you equate that differential coefficient to 0. It is a method of optimizing, either minimizing or maximizing. You will see that here we want to minimize, and we equate d by dn of T of n equal to 0. Okay, and that will give you, you differentiate this. When you differentiate this, lambda into s square is a constant, and the only variable for differentiation is small n, and the first term when differentiating will give you minus lambda into s square by n. Then next term, second term is constant, third term is also a constant, but the fourth term is a function of n, and when differentiating with respect to n, it will be C1. So you will get minus lambda square by n square plus C1, that is equal to 0. And you can solve for n. First you will get n square is equal to lambda into s square divided by C1, and you take the positive square root, that is equal to root of lambda into s square by C1. Why you are taking positive square root? Small n is an integer, either 1 or 2 or 3 or like that. It cannot be negative, therefore you take the positive square root. Okay, and you have only one value for n, and you can easily check that for the second derivative. If you substitute this value, it will be greater than 0 for minimum of total cost T of n. Okay, that is how you find the sample size small n. ഇവിടെ നിങ്ങൾ ശ്രദ്ധിക്കേണ്ട ഒരു കാര്യം, ഇവിടെ നേരത്തെ മെത്തേഡിൽ, അതായത് നമ്മൾ ആദ്യം കൺസിഡർ ചെയ്ത മെത്തേഡിൽ രണ്ട് കാര്യങ്ങൾ സ്പെസിഫൈ ചെയ്യേണ്ടിയിരുന്നു. ഒന്ന്, അതിൻ്റെ മാർജിൻ ഓഫ് എറർ എപ്സൈലൺ, പിന്നെ കോൺഫിഡൻസ് കോഎഫിഷ്യൻറ്റ് 1 മൈനസ് ആൽഫ. ഓക്കെ, if it is expressed in percentage, it would have been 1 minus alpha into 100%. ഈ രണ്ട് ക്വാണ്ടിറ്റി വെച്ചിട്ടാണ് നമ്മൾ z ആൽഫ ബൈ 2 ഒക്കെ കമ്പ്യൂട്ട് ചെയ്തിരുന്നത്. ഓക്കെ, ഇവിടെ പക്ഷേ നമ്മൾ അതൊന്നും ചെയ്യുന്നില്ല, മറിച്ച് നമ്മളൊരു കോസ്റ്റ് ഫംഗ്ഷൻ ഡിസൈൻ ചെയ്യുന്നു, അതുപോലെ ഒരു ലോസ് ഫംഗ്ഷനും ഡിസൈൻ ചെയ്യുന്നു. ലോസ് ഫംഗ്ഷൻ നിങ്ങൾക്ക് ഇഷ്ടം പോലെ ഡിസൈൻ ചെയ്യാവുന്നതാണ്, അതേപോലെ തന്നെ കോസ്റ്റ് ഫംഗ്ഷൻ നിങ്ങൾക്ക് ഇഷ്ടം പോലെ ഡിഫൈൻ ചെയ്യാവുന്നതാണ്. And using that cost function and loss function, you can find the value, optimum value of small n equal to root of lambda into s square divided by C1. Okay, thank you.